In the previous class, we had discussed a difference between Coulomb's law and gravitational law. The force between two masses is independent of medium between them, but the force between two charges is dependent on the medium between them. Means when you have two charges and they are placed in vacuum and then they are placed in water, the force is going to be changed, right? Now, there is a statement which is always told that force between two charges is independent of presence of third charge.
Yes, sir. Yeah, if you keep like a charging between them, then
So this statement is a little trickier one. The force is not going to change. The net force is going to. When you have two charges in vacuum, they will experience the same force in water because of each other, but the medium will be polarized. The medium will cause some charges, some more charges to grow up, and they will change the net force between these charges. So a medium gets polarized, and due to that only the net force changes. So let's just quickly talk about that what I'm talking. In chemistry, you must have heard about polar and non-polar molecules. So tell me, what is a polar molecule? And what is a non-polar? No idea?
the polar molecule are like molecules in which like the positive and negative charges do not coincide.
Coincide. Okay. What is water? It is a polar or non-polar molecule?
The water is polar molecule.
Right. So we have a concept like dissolves like.
Yes, sir. Yeah, it is in inorganic. Yeah.
Means polar liquid will dissolve a polar solute.
Yes.
And non-polar will dissolve a non-polar solute. So let's talk about a polar molecule. First of all, let's just take an example of H2O. So in H2O, we know that oxygen can attract more electrons towards itself. So when hydrogen and oxygen are going to make a bond, you can see there will be a little bit of partial negative charge on the oxygen, and there will be partial positive charges on hydrogen, right? And a positive negative charge combination creates a dipole moment. So what will be the direction of dipole moment?
So from positive to negative.
From positive to negative. Sure. We are not in chemistry. In physics, the direction is opposite. In physics, we take the direction of dipole moment opposite to chemistry. It is from negative to positive. Forgot? Like you have a negative charge and a positive charge. So dipole moment will be in this direction. If you are in any doubt, just go and clear this from, derivations of electric field at equatorial and axial position. We take the dipole moment from negative to positive, and in chemistry, it's opposite. Like the work done in thermodynamics.
Okay, so yeah, I was considering.
It's okay, but you have to remember that here, because in NCERT, it is, proved, written. So it's in our syllabus. Now, we can see that there is a net dipole moment. We have a net dipole moment in the downward direction. Or let me take another example, another simple example like of HCl. So which one will have a partial negative charge?
Chlorine or Cl.
Chlorine. So let's just make a negative charge in here and a positive charge in there. So you can also see here there will be a net dipole moment developed.
Yes, sir.
Oh, okay. I'm looking like a ghost. And electricity has just gone.
Okay, sir.
And I'm experiencing earthquakes, one per day.
Really?
Yeah. There was one yesterday. There was one today. So let's see whether it is an AP or GP or an HP. Okay. Yeah, that earthquake will do whatever it wants to do. I cannot. Never mind. Sorry. Now you can see these molecules are already polarized. The HCl molecule, the HF, the H2. So there is no need for you to polarize these molecules. But let's just talk about some non-polar molecules. Can you give me an example of non-polar molecule?
So simple oxygen O2 or N2.
Yes, right. Oxygen, nitrogen, these simple examples, these like molecules. So we can see there are no partial positive or partial negative charges. The net dipole moment of a molecule is already zero. Okay, right?
Yeah.
So now, why are we talking about such molecules? First of all, let's just say we have an electron cloud surrounding the nucleus. In an atom, there is a nucleus at the center and electrons revolve around it. So the path, the trajectory of electron, all that makes an electron cloud.
Yes, sir.
Okay. The circular spherical region, we call it an electron cloud. Now, I have two kinds of molecule. One is polar, one is non-polar. So in polar, you have seen that there will be a dipole moment. So I am making a shape which is looking like a dumbbell. So when you have a polar molecule, you will see there are slight positive and negative charges which are present, which are already present in that molecule. So the electron cloud is a little distorted. On one side, you can say there is a little bit of excess of electrons. On one side, there is a deficiency.
Yes, sir.
Now, when we discuss about a non-polar molecule, so in a non-polar molecule, the electrons are uniformly distributed. We can say that.
Yes, sir.
So here, the net dipole moment will be zero. And in the previous case, the net dipole moment wasn't zero. So that's how you denote the polar and non-polar molecules present inside a material. Now, let's see what happens when I turn on an external field. You know, it has a dipole moment of its own. So it will have an electric field associated with itself too. Electric field at axial, equatorial, or at some angle theta. So I'm not talking about its own electric field for now. I'm talking about the electric field that can be given from outside. So let's just say I have a non-conducting material. Okay. What is the another name for a non-conducting material? It is dielectric. Insulator, yeah. But here we use dielectric when we are talking about polarizations, how much a material will be polarized. Now, let's just say I have a material which is made up of many molecules, and these molecules are polar molecules. So you see, when you have water in bulk, the water doesn't show you its dipole moment. A single molecule can, but not all the combination of molecules. They are not going to show you any dipole moment. Why is that? Yes, exactly. So those dipole moments are aligned in random directions. Okay. So you can see the dipoles are aligned randomly. Initially. And just for a little bit, let us look at this reason. There will be like infinite number of molecules present. Okay. Yes. Here you can see I have chosen a region and all the dipoles are pointing in the same direction, right? So yes, this region is called a domain. In physics, in chemistry, we call this region as domain. If you study your first chapter of chemistry, which is solids, it is mentioned in there that domains are the regions in which the molecules are likely aligned. The dipole moment points in the same direction. So when you are going to throw molecules randomly, there will be some reasons in which a certain number of molecules are pointing their dipole moment in the same direction. Okay, so it can happen. Now, what is domain? So you can write it domain is a region in which some dipoles are aligned together. Some certain number, their number will be significant, like 1% or 2% at max. Okay, they cannot be like 50 or 60%.
1% of infinity is very big. So
Exactly, there will not be infinity amount.
yes,
There
sir,
cannot never be
margin.
infinite.
Yes, sir.
Like if you have taken 1 meter cube, there can be 10 raised to power 28 molecules in it. So it's a significant number and it's very large. We will not be able to determine it. Hence, I am calling it as an infinite number. What is infinite? That cannot be measured.
Yes, sir.
Okay. Now, what happens when you turn on an electric field, when an external electric field? So let's just say I have an external electric field, which is called E naught. I turned it on. Now, let's just say you had a dipole which was pointing in this direction. When you turn on an external electric field, in which direction is this dipole going to point? Do you remember
It will
something
be in
about?
the
Yes.
That will be the direction of the field.
Right? Why? Why would this molecule point itself towards electric field's direction? The reason is simple. It will try to attain a stable equilibrium.
Stable equilibrium, yes, sir. Yeah.
So to reach the stable equilibrium, this dipole will try to align itself in the direction of electric field if it is free to move. Okay.
Yes, sir.
So you can see conductors are more conducting, their dipoles are more free to move in the direction of electric field.
Understood.
So this will align to external electric field. Now, it was for a single dipole. What happens when I place all the dipoles, all the bulk in the same electric field? This is our external electric field E naught. And now I have put the dielectric, our substance, our material, into the direction of this electric field. So you can see the dipoles, whatever the number, will try to align itself in the direction of electric field. Some dipoles can be found not in the direction of electric field due to the low magnitude of external electric field or their inability to rotate. It can also happen. Okay, but most of the dipoles will be aligning themselves along external electric field, right? If I explain this to you in terms of electron cloud, you can see the electrons cloud that are formed will be looking like a dumbbell shaped in this negative, positive, like this one. So there will be a lot of electron clouds. In the end, we will just have a glimpse at the NCRT. Okay. So this is the real diagram that how polar molecules align themselves. Next, let's talk about non-polar molecules. So a molecule can be ionized, any molecule. Let's just say you have a non-polar molecule. So in non-polar, there will be a positive charge at the center and the negative charge will uniformly be surrounding the positive charge. Now, we know that force is parallel to electric field on a positive charge. When you have a positive charge, the force experienced by the charge will be in the same direction as that of electric field.
Yes, sir.
But if the charge is negative, so the force and electric field will be in opposite direction. So let's just say in this scenario, I turned on an external electric field E naught. An external field is switched on. So you can see this external field will try to throw the positive charge on the right hand side. The positive charge will try to move, yes, and the negative charge in the opposite direction. So again, this body will take the shape of a dumbbell like this one. So here will be a positive charge, there will be a negative charge. So the non-polar molecules will certainly take a shape of dumbbell.
Yes.
And you can say the polar molecules, they were already in the shape of a dumbbell. So electric field didn't need to change their shape a lot. Okay.
Yes, sir.
Now, if you turn on the external electric field to, polar or non-polar, you can see all their dipole moments. First of all, if they don't have a dipole moment, they will form a dipole moment, and then they will be aligned in the direction of electric field. Okay, so that's how you polarize a dielectric substance. Polar molecules can also be dielectrics, non-polar as well as. Okay. So this was a little bit of weird theory, but you have to study about it.
Yes, sir.
Right. Any other doubt in this topic?
No, sir. Understandable.
Now, see, we have a symbol which looks like this one. This symbol is called what? Epsilon. And what does it denotes? This symbol is taken from Greek letters. Yes, it denotes permeability or permittivity. Permittivity of which medium?
Like any medium, it is
any medium, right? It can be used for any medium. Now, there is a symbol which is epsilon naught. So it denotes permittivity of free space. It is for vacuum only. You cannot use this symbol for any other medium. Now, when a medium is put between charges, the charges will have their own electric field, and that electric field is going to ionize, polarize our medium.
Yes, sir.
So there must be some ratio, some index that is going to tell us how much a medium is going to be polarized. For example, when we have metals, we know that metals will be polarized maximum. When you have wood, wood will be polarized minimum. So there should be a certain index, a certain number that should tell us how much a medium will be polarized. So for that, we come up with a ratio. Okay. So we have epsilon over epsilon naught, the ratio of permittivity of a medium as compared to permittivity of free space. Okay. And it is denoted by epsilon r. So this epsilon r denotes relative permittivity. You just say it as relative permittivity, but it is relative permittivity of that medium as compared to, right, vacuum. Right?
Yes.
Now, remember that epsilon is equal to epsilon r into epsilon naught. There is a chapter, the 5th chapter in your syllabus, in which we will be talking about this formula a little more. Now we only have to deal with the electric field. In that chapter, there will be electric as well as magnetic field.
Okay.
So there will be some more symbols. Right?
Yes.
Now, the epsilon r, or there is another symbol which is K. So this K denotes dielectric constant. So when you are going to hear about relative permittivity or dielectric constant, they both mean the same thing. These are just different numbers. Dielectric constant, it is directly for the medium, that how much the medium is with respect to vacuum, how much the medium is going to be polarized.
Okay.
So these are just different symbols. Just while using the formula of forces or electric field or potential, do not use the symbol K, because now we have two Ks. This K is Coulomb's constant. This K is our force constant in here. So this constant is different a lot from dielectric constant.
So the value is 8.854 for this, right?
The value of this K is 9 into 10 raised to power 9.
Okay, yeah.
The value of this is 8.85 10 raised to power minus 12.
Yes, sir.
Please do not be confused. We have a lot to cover and this is just the second chapter.
Yes, sir.
Now the trick is, whenever you change the medium, replace epsilon naught with epsilon. Okay. Now, here's a question for you. We have two charges, Q1 and Q2, placed at certain distance R. So these are placed in vacuum. So what do you think will be the force between them? So I will say the force is, don't use K here, okay?
Okay, yeah, 1/4 by epsilon naught.
Q1, Q2 over R square. So I am calling this as FV, or you can say force in vacuum. Now, another question. You have two charges, Q1 and Q2, but now they are placed in a medium. And the relative permittivity of medium is epsilon R, you can call it, or you can say it's dielectric constant is K. So what do you think will be the force in the medium? So when I say what will be the force between them in the medium, I mean what will be the net force? Okay, because now the medium is polarized. So the medium will also cause some forces on Q1, some forces on Q1 and Q2 each.
Yes, sir.
So Q1 will attract Q2 with the same force as it was attracting or repelling in vacuum. But the presence of other charges will change the net data. The presence of other charges will cause superimposition of forces. So the net force will be what? Tell me.
So 1/4 by epsilon naught into epsilon naught R.
Yes. So instead of using epsilon naught, use epsilon, because
Yes, sir.
we are not in vacuum. So you can also call it Q1, Q2 over R square. Now divide the force in medium to, okay, let's divide the force in vacuum, because we know force in vacuum will be more, to force in medium. What will you have? What will you have?
Sir, epsilon by epsilon naught.
Right. Epsilon by epsilon naught. And what this quantity is?
Sir, relative permittivity.
Right. So you can say the force in medium is equal to the force in vacuum divided by relative permittivity. So relative permittivity is nearly 81 for water. In some books, they call it 82, but generally we take it as 80. We call the relative permittivity of water as 80 because it is, a little bit convenient in our numericals. So it's 81, but you can use it as 80. So you can see when you have 80 coulombs of 80 newtons of force in vacuum, that force will be reduced to 1 Newton in water. And that will be the net force. The medium will be polarized. So that polarization causes that field to reduce. Right? Now, sometimes they also ask a certain question. We have Q1, we have Q2, and they are placed in a certain medium of relative permittivity as epsilon r, and the distance between them is r. The question is, what force is exerted by Q1 on Q2? They are in a medium. But
So then we, sir,
yes,
then
yes,
should be 1 by 4 by epsilon not Q1, Q2. So because we are not considering the medium's force.
exactly, exactly. So when you are placing them in a medium, there will be some dipole moments developed in this medium. And these dipole moments will apply forces on these charges. And in the beginning, I told you a statement. Force between two charges is independent of third charge, right? So they will exert the same force on each other. So the net force is changed, but the individual forces aren't.
are same. Yes, sir.
Right. Okay. So, there is a lot to think how they present a question to you.
Yes, sir.
Any other doubt?
Understood.
Okay. Now, this was for two charges. Let's talk about a bulk. Let's talk about what is going to happen when you are going to use dielectrics. So you see, if I had a vacuum, I used epsilon naught. When I had a medium, I replaced epsilon naught with epsilon, right?
Yes, sir.
So do it wherever you can. A quick question for you. The question will be regarding this chapter. So you have a capacitor and the area of plates of capacitor is A and the distance between plates is D. Now tell me, what will be its capacitance? There is air, or you can say vacuum, present between the plates. What will be the value of capacitance? What are you doing?
So no,
You forgot
no, sir.
the formula?
No, sir, I remember the formula A epsilon not D by, AE epsilon by D.
Right. You can call it A epsilon naught. I have just a habit of saying epsilon naught A over D.
Okay.
So you can see this is capacitance in vacuum, right? Now, what happens when I replace the vacuum with a certain medium? What will be the formula now? What will be the capacitance?
Sir, epsilon not A by D. So not epsilon not, epsilon into A by D.
Right. So now we are in a medium. So instead of using epsilon naught, which is exactly for vacuum, we will use epsilon. So you can see the capacitance would be this one, right?
Yes, sir.
Now, a combined question for you. A medium, a capacitor, This is a very important question. You will be seeing it a lot in the full chapter. A capacitor of capacitance C, okay, is present. Now you put a medium of dielectric constant K inside it. You know, find new capacitance. So if I compare this to the upper question, the capacitance was C in this scenario. What will be the value of capacitance now in terms of that C? Got it?
Sir, K into epsilon naught.
Right. Now, if I divide these two, I will have epsilon over epsilon naught, which is our epsilon R, which is also called K, dielectric constant, right? So I can say capacitance in medium is K times capacitance in vacuum. So in here, our answer would be new capacitance will be K times the older capacitance. Or you can see new capacitance. First we had epsilon naught A by D. How do you change epsilon naught into epsilon? By multiplying it with epsilon R. This term K epsilon naught
Yes.
is epsilon.
Okay,
So
yes,
just
sir.
please remember these formulas. And out.
Sir,
Okay. Now, we know if we have a capacitor, what is the value of electric field present inside a capacitor? What's the value of electric field in terms of sigma?
Sir, sigma by 2, so sigma by epsilon naught.
Right. Now, what happens when I put a medium in it? What happens when I have put a medium of dielectric constant K in it?
Sir, sigma by K epsilon naught.
Right. So the net electric field would be sigma by epsilon. When in medium, we just have to replace epsilon naught with epsilon. And you can say the answer would be epsilon naught K, this one. Any doubt?
No, sir, understood.
Right. Sure.
Yeah, understood.
Okay. Actually, today we are dealing with a lot of theoretical questions. Now, let's begin. Polarization of a dielectric. That means how much a dielectric can be polarized. So we have a term which is called polarization, and we denote polarization with capital P. So polarization is defined as net dipole moment per unit volume. Okay, so it's given as P net, this is small p, divided by volume. I'm not going to use the symbol V for volume because of potential difference. Now, let's just say I have a medium in which dipoles are randomly aligned. So what can I do to make all these dipoles align in a single direction?
So like introduce a uniform electric field in the particular direction.
Exactly, right. So I have turned on an external electric field. What if the external electric field is very, low? Its magnitude is so less. You can say it as feeble, of very little amount. Will it be able to rotate the dipoles?
No, sir. You would need a very strong electric field.
Exactly. So I can say if I increase the electric field, the more dipoles will align in the direction of electric field. So can you say it that the polarization is directly proportional to external electric field E naught? The more the electric field, the more will be polarization, up until a certain limit, of course. Or any doubt is there?
No, sir.
Now, sometimes we have to match the units also. So we have to multiply this with epsilon naught. Electric field is what? Sigma over epsilon naught. So sigma is what? Electric field into epsilon naught. This one. So it's also given. Means the more the electric field, you can see more charges being developed on the dielectric. Now, what happens when we remove the proportionality? Sorry, just a minute. Yeah. What happens when we remove the proportionality? So there will be a constant, and that constant is called with this symbol. Have you seen this one?
Xi.
Yeah, chi. This symbol is KII, chi. Some people call it chai, but chai is a little different. There is chai, there is chai, then there is psi. Who knows about phi? So this symbol is called chi. I have seen some people calling it with some different names, but I have, hold my investigations and it's Kai. Kai, like the Kung Fu Panda villain.
Yes.
Have you seen that movie? The
Yeah,
third part.
lost like long time ago.
Yeah, there was a villain in the third part, Kai, who's returned from hell or some trance state, I don't know. Now, we have this symbol Chi. So remember that this Chi is unitless, first of all. And this Chi is also written as Chi E, which means electrical susceptibility. Chi denotes the extent up to which a material can be polarized.
Yes, sir.
So this Chi is susceptibility. We are going to talk about it in 5th chapter. There will be a 5th chapter which is called magnetism and matter. Magnetism. So in that there will be magnetic field, and you will be told one more formula, that dielectric constant or relative permittivity is susceptibility plus 1. So its chapter is in the fifth, its proof is in the 5th chapter. So just remember this one for now.
Okay, sir.
So who will have more value of susceptibility, wood or metal?
So metal.
Metal, right? So if a material can be polarized more, its susceptibility would be more. And in that 5th chapter, you will see if a material can be magnetized easily, its susceptibility would be more. So now we are trying to develop charges. In that chapter, we will be trying to develop poles, North Pole, South Pole, magnetic field lines. Okay. Now, see, let's just say I have a material. This material is a dielectric, and I have placed it inside an external electric field. Be very careful about the derivation. So, you know, the electric field outside is, let's just say, sigma by epsilon naught. And the dielectric constant of this material is K. So what do you think will be the net electric field inside this material? Because here you can see we have vacuum.
So sir, it should be sigma by epsilon naught K.
Right. So it will be sigma by epsilon naught K. And I have called it as net. That means there is some polarization. So you can see this whole material is acting as a single dipole. So in a dipole, you know, there are some positive charges developed. Here will be some positive charges developed on this side, because electric field will try to push the positive charges in its own direction and the negative charges in opposite direction. So some charges will be developed on the dielectric. And these charges are called polarized, or you can call it induced charges. And what do you think is the direction of electric field due to these induced charges? What should it be?
Sir, it should be in the direction of the external electric field.
Right? Why?
So because it's polarized.
Okay. You have two charges, one positive, one negative, and these are induced charges.
Yes, sir.
Just forget that you have external electric field. What's the direction of electric field in terms of charges?
That is from positive and negative.
So this is the direction of induced electric field. Now you can see when you had the dielectric, okay, there was external electric field present inside it, E naught. There is an induced electric field present inside it, and these are in opposite direction, so they will cancel it out a little bit, and you can see there will be a net electric field inside, right?
Yes,
so just remember that net electric field should be vector sum of external electric field plus induced electric field. Remember that vectors are only added. Their values are added or subtracted. We call it vector sum, superimposition. So I am not giving you a negative sign even after knowing that these are in opposite direction. So it will be written like this one. And when you will put the values, you know all the electric fields are in x-axis. So now we don't need the vectors I cap or j cap. So the net electric field would be the external electric field minus the induced electric field. You can call it as this one, right?
Yes, sir.
Please write this one. Actually, you cannot solve numericals without knowing everything that's happening in a numerical. Sometimes when you know the theory behind it, you can also make some educated guesses. Like if the value of dielectric is 1, 0, infinity, something like this one.
Yes, sir. Yes, sir, done.
Right. Now, if I ask you, tell me what is the value of induced electric field? You would say induced electric field is external electric field minus net electric field.
Sir.
So I had assumed our external electric field as sigma by what? Epsilon naught.
External node, yes, sir. And E net
And you
is,
told me, yes, it's what?
sir, it's external node K.
Right. Got it?
Yes, sir.
You can also use this one from here. You can also say induced electric field is equal to external electric field plus, minus net electric field. And we know that, can I write it like this one?
Yes,
You
sir.
know, this one is external electric field. And when I divide external by K, it will be this one. Okay.
Yeah.
So it can also be stated as like this one. Induced electric field is equal to E naught bracket 1 minus 1 over K. You can call sigma by epsilon naught. You can take them at, sorry, external disturbances. Are you hearing this one? These songs?
Yes, sir, there is some sound, but there is not. It's not clear. It's like distorted.
Okay. Actually, I've been a little distracted. I'm thinking, which song are they singing? First of all, this thing is coming to my mind and I'm losing my focus. Never mind. Okay. So we use this formula. Got it? Any problem? Now, you can see electric field is sigma by epsilon naught. And this electric field is due to induced charges. So I can say induced surface charge density by epsilon naught. Now cancel the epsilon naughts. So you will have induced is equal to sigma 1 minus 1 by K. This is also an important derivation. And we know sigma is what? Charge by area. So you can also say induced charges are equal to inducing charges 1 minus 1 by K. So I'll just write this one. I'll explain this one.
So what is the
And we
capacitance?
are, I will explain. I'm talking about magnitudes here only.
Yes.
Got it? Okay, see. First of all, a question. Let's just say you have a dielectric and you brought just a single plate of a capacitor. So let's just say this plate has a charge positive Q, right? So due to this positive Q, there will be some induction of negative charge on this facing side, right?
Yes, sir.
So I'm going to call it as Q, not minus Q, Q. So this Q denotes induced charge, right? And this Q is called inducing charge. Now, what if this dielectric is actually a metal? There will be a lot of induction.
Yes, sir. Yeah.
What if this dielectric is a wood?
Then less.
Q would be 0.
Yeah, almost. Yeah.
So how to find how much charge will be developed due to induction? So charge due to induction will be capital Q, 1 minus 1 over K. And if you use proper signs, there will be a negative sign, because we know the induced charge is of
negative.
opposite nature.
Yes, sir. Yeah.
Got it?
Yeah.
Now,
so the induced charge can be negative as well, right? I mean, sorry.
Induced charge will be of opposite nature to inducing.
Yeah.
So if I had brought a negative plate, so induced charge would have been positive.
Positive, yes, sir.
So that's how this formula comes. It is also an important formula. I also have shown you the derivation. Now, please have a very quick revision about this one, because you will not be given a simple question in IITs. Now, range of epsilon R. What's the range of relative permittivity, or you can say dielectric constant? So we know that epsilon R is equal to what? Epsilon R is epsilon over epsilon naught.
Yes, sir.
And this denotes kind of polarization, how much medium is polarized. So what happens if I take the medium again as vacuum? I can take any medium. Epsilon can denote any medium.
Yes, sir.
So epsilon R is equal to 1 for what? Vacuum.
Vacuum.
And if you have a material can be induced, polarized to any extent. So value of epsilon R is infinity for metals, or you can say conductors. So what should be the range of K or epsilon R? So the minimum value of dielectric constant is 1, and its maximum value can reach infinity. In physics, we cannot, in maths, we cannot put a thing exactly equal to infinity.
Yes, sir. Yeah. It tends to
limit.
Yes, sir.
Yeah. So the range of K is between 1 to infinity. 1 is for vacuum, means you cannot polarize vacuum. Why cannot you polarize vacuum?
Because there are no molecules.
Exactly, right. So for polarization, we need molecules, polar or non-polar, at least some molecules.
Yes, sir.
Can you prove it? Vacuum cannot be polarized. So we know that. Actually, we don't know that. We are just assuming that. K is equal to chi plus 1. So for vacuum, K is equal to 1. So chi will be 0. Polarization is chi epsilon naught into electric field. So you can see the polarization will be 0. Got it?
Yes, sir.
So that would be all for today. In the next class, maybe we will talk about displacement vector. It's just a heading given in the NCERT. It is never asked in any question.